Welcome to lesson 3.4. We are going to be solving exponential and logarithmic equations using the properties that we've learned previously in the chapter. So objectives, we're going to use like bases to solve exponential equations. Then we're going to use logarithms to solve exponential equations. And we'll talk about which strategy works best and what scenario you're presented with. Then we'll solve logarithmic equations by using the definition of a log, and then using the one-to-one property of logs. And then we'll look at some applications. All right, so the first part of the objective was how to solve by expressing each side as a power of the same base. So what you need to know is if you have a situation where if b raised to the power of m is equal to b raised to the power of n, then m equals n, right? So if the bases are the same, then those two exponents have to be the same as well. So you got to rewrite it in the form of b to the power of m is equal to b to the power of n. What that means is you got to get the bases to be the same. Once the bases are the same, then you set the exponents equal to each other, then you solve for the variable. So let's look at the examples we have. I'm going to demonstrate part A right now, and then I'll have you try B, C, and D and on your own, and then we can compare answers. Give me 1 second. All right. So do that to get a pen. All right, so let's start with part A. 2 raised to the power of 2x minus 8 is equal to 16. I need that 2 and that 16 to be the same. So what I'm going to do is I'm going to rewrite 16 as 2 to the 4th power, because 2 to the 4th power equals 16, and then the bases are the same 2's. So you got 2 raised to the power of 2x minus 8, and that's equal to 2 to the power of 4. Since the bases are the same, the rule is now that the exponents have to be the same. So I can simply write now 2x minus 8 equals 4. Now I'm solving for x. Add 8. You get 2x is equal to 12. Divide by 2, you get x is equal to 6. Okay? So what, I'm going to do part B because there's something I want to show you about this that's a little different than part A. So in part A, we only had to manipulate one of the sides, right? Because I could turn 16 into 2 to the power of something, right? Well, 27 and 9, I can't turn 9 into 27. Like, there's not a power I can put on, well, there's not an integer power I can put on 9 and make it 27. But what you can do, let me just change the color here, separate it. What you can do is manipulate both of them, because they are both powers of 3, right? 27 is 3 cubed, 9 is 3 squared. So what you can do is turn 27 into 3 cubed, and you can turn 9 into 3 squared. Now the bases are the same, and I can now set the exponents equal to each other. So 3 times x plus 3 is equal to 2 times x minus 1. I can distribute, well, now I'm just solving a linear equation, right? I'm going to distribute, I got 3x plus 9. Here I've got 2x minus 2. Let's subtract the 2x, and you get x. Subtract the 9, and you get negative 11. All right, so for part B, the answer is negative 11. Why don't you try parts C and D? So pause it, try those, and then come back and we'll go over the answers. So for part C, I turned 125 into 5 cubed. Now the bases are both 5. 3x minus 6 equal to 3. Except the exponents equal to each other. Solve for x and got x equals 3. For part D, I changed both bases. I changed 8 into 2 cubed. I changed 4 into 2 squared. I now set the exponents equal to each other, solve the linear, and got x equals negative 12. All right, let's take a look at the next example. So now the other way to solve an exponential equation is you use logs to solve them. So not every exponential equation you get is going to have bases that you can manipulate the way that we just did. So if you can do what we just did, that is the easiest way to do it. But in a lot of cases, you're not going to be able to do that. So here's the alternate way to do it. So you isolate the exponential expression, and then you take the common log of both sides. If the base is 10, you take the natural log if it's any other base. Honestly, it doesn't really matter. Definitely, well, I will say definitely take the common log if the base is 10, and definitely take the natural log if it's base e. Otherwise, it actually doesn't matter. But anyway, that is one way to do it, though, is just to do common log for base 10 and then natural log for everything else. Then you're going to simplify using one of the properties, depending on which type of log you took, and then you solve for the variable. So let's take a look at this in action. Oh, I went too far. All right. So the first equation here is 4 to the power of x is equal to 15. So again, situation where if that was 16, I could turn 16 into 4 squared, and then I could say that x equals 2, right? But it's not. I can't turn 15 into anything that relates to 4, right? So I can't do what I did with the last example. So what this is suggesting is you take the natural log of both sides. So here's what that looks like. Okay. What we're going to use now is the power property that we learned in a previous lesson. So that x that we're trying to solve for, I'm using the power property. An exponent on the inside becomes multiplication on the outside. So now x times natural log of 4 is equal to natural log of 15. Now I can divide both sides by natural log of 4. And then x is equal to natural log of 15 divided by natural log of 4. If you needed to simplify that, well, I guess simplify that, right? Round that. So like this is the exact answer. It's natural log of 15 divided by natural log of 4. But if you needed to round that, I'm going to use my calculator real quick and find out what that is. So I use my calculator. When I rounded the nearest hundredth, I got 1.95, so 1 and 95 hundredths. So what that answer means, by the way, is that is the exponent you put on 4 to get 15. That answer makes sense, right? Because 4 squared is 16. So something slightly less than 2 is going to get you an answer slightly less than 16. So it just depends on, I'm sure you'll have some questions in Math Excel where it wants the exact answer, like for you to give it in terms of the logs. Or it may ask you to round it, and it may ask you to round it to wherever on the decimal scale. But just make sure you're following directions, make sure you're answering what it's asking you to give. So you don't want to like round it when it's asking for the logs or whatever. All right, so why don't you try parts B and C, and then we can come back and check. So looking at part B, take natural log of both sides, use power property to get the x out, divide both sides by natural log of 5, and you end up with natural log of 134 divided by natural log of 5, which rounds to 3.04. When the base is 10, remember we suggested using common log of both sides. When you do that, and I'll show you in 2 steps why, take the log of both sides, so that's the same thing. Use the power property, that's the same thing. So now you've got x times log of 10 is equal to log of 8,000. Remember that common log means base 10, right? So the exponent you put on 10 to get 10 is 1. So log of 10 is an expression that equals 1. So x times 1 is just x. So essentially, that part goes away. And you just got x is equal to log of 8,000, which rounds to roughly 3.90, rounding to the nearest hundredth. All right, let's take a look at the next set. All right, now we're going to look at log equations. So some of them will be able to be solved by using the definition of a logarithm. So basically what you would do is take a log equation and rewrite it as an exponential, which would then allow you to solve for the variable. And then you can check the solutions in the original equation, and you're only going to include the ones where once you substitute the variable back in, that it makes the m value greater than 0, because remember that can't be negative. So let's take a look at the first example. So if you have log base 4 of x plus 3 equal to 2, I'm using the definition of logs. So what does that mean? All right, so I'm going to basically turn it into an exponential. 4 is the base. 2 is the exponent. And it's set equal to x plus 3. Now I just have an equation I can solve for x. 4 squared is 16. Subtract 3, and you get x is equal to 13. All right, so that was part A. All right, let's take a look at the next part. All right, part B. You have 3 natural log of 2x is equal to 12. First thing I would do is divide 3 from both sides. Now you've got natural log of 2x is equal to 4. Remember what it means for a natural log. That means the base is e. 4 is the exponent, is equal to 2x. So when I divide both sides by 2, you have x is equal to e to the power of 4 divided by 2. That would be your exact answer. If you needed to round it, I'm going to use the calculator real quick. You get 27.299. Again, it just depends on what the question's asking, if you want the exact or if you want the rounded answer. Okay. Why don't you try C, D, and E, and then come back and check. Part C, use definition of log. I rewrote it as 2 cubed is equal to x minus 4. And then solve for x and got 12. Part D, that was closer to like the part B that I had previously done. Start by dividing by 4, then use definition to get e squared is equal to 3x, divide by 3. E squared divided by 3 is the exact answer. 2.46 is the rounded answer. And then for part E, just use definition, get 2 cubed is equal to x plus 20, solve for x, and you get negative 12. All right, let's take a look at the next one. All right, next set is using a one-to-one property. All right, so you express the equation in the form one log equal to another log. So you want no coefficients, or I guess a coefficient of 1 on one side. Then you use a one-to-one property to rewrite the equation without logarithms. So if you have the base the same on both sides, it's similar to like when you have two exponential expressions with the base is the same, then the exponents have to be the same. Then you solve for the variable. And you can go back and check to make sure that it doesn't make the expression negative. So let's take a look at an example. Let's do part A together. So you have natural log of x plus 2 minus natural log of 4x plus 3. And then that's equal to natural log of 1 over x. First thing you need to do is condense. So the condensing we did last lesson. We're going to do here subtraction on the outside becomes division on the inside. So that means natural log of x plus 2 minus natural log of 4x plus 3 is equal to natural log of x plus 2 divided by 4x plus 3. And that's still equal to the other side where it's natural log of 1 over x. Because it's the same base, which in this case natural log is base e, I can say now that this is equal to this. So you can say x plus 2 over 4x plus 3 is equal to 1 over x. Best way to solve this would be, you've got a proportion, set cross products equal to each other. So x plus 2 times x is going to be, I'm going to rewrite it up here, x squared plus 2x. And then 4x plus 3 times 1 is equal to 4x plus 3. Now I've got a quadratic to solve. All right, so I'm going to set everything to one side by subtracting 4x and 3. So you got x squared minus 2x minus 3 equal to 0. Can this be factored? I think so, off the top of my head. So let's take a look. Trying to get multiply to -3 and add the -2. So you're going to have x minus 3 and x plus 1. So that means x is equal to 3 and x is equal to -1. When you go back to the original, remember you can't have any part of, like, you can't have any of these expressions be negative. So if I substitute 3, in there it's 5, in there it's 15, in there it's 1/3. So that one looks good. If I substitute -1 in for x here, -1 plus 2 is 1, so that's okay. But -1 in here makes that -4 plus 3 is -1. So it makes that expression negative, which it can't be. So x equals -1 is not a good solution. So the only solution here is x equals 3. Okay. For part A, x equals 3. Why don't you try part B and then come back after you unpause and we can check. So for this one, used quotient property again to create that. Now I set both parts equal to each other. So x minus 3 is equal to 7x minus 23 over x plus 1. Multiply both sides by x plus 1. So it cancels out on the right side, and you have FOIL on the left side, and I got x squared minus 2x minus 3. Brought everything to the left side. Got x squared minus 9x plus 20. Factored that into x minus 4 and x minus 5. So when I solved, I got x equals 4 and x equals 5. Tested both 4 and 5 in each of the expressions, and they all work. So that means 4 and 5 are both solutions. All right, let's check out the next one. All right, so we're going to look at two different flow charts to see, basically just break down what we've just done. So if you go back to the first two parts of the objective, the two different ways to solve exponential equations. First thing you're looking for is, does it have the same base? If it has the same base, then you simply set the exponents equal to each other and solve. If they don't have the same base, then can you make it the same base? So like if one base is 2 and the other base is 4, well, you can turn 4 into 2 squared, right? And if that's the case, then you set the exponents equal to each other. If you can't, then you got to apply common log or natural log to both sides and then solve. For a logarithmic equation, can you apply the definition of log? If you can, that's the easiest way, and you just solve. So that was like 2 examples ago. If you can't, then you use properties of logs to simplify, and then you can use a one-to-one property. So that's what we just did, right? And then either way, you're applying the definition of log at the end. So David and Jordan, well, now we're gonna, okay, last part of the objective is looking at some applications. Okay, so David and Jordan will inherit $30,000 at age 20. They're going to take 25,000 of that and invest it at a rate of 9%. So an annual rate 9%, that's compounded monthly. And they plan to have over $500,000 for early retirement. So is that possible? I guess what we need to figure out is how long will it take for $25,000 invested that way to turn into $500,000, and then we'll see if it's reasonable that they could retire. Retirement age is around 60, 65, somewhere around there, right? So if that's the age we get, then I guess it would be reasonable. Is it possible? Yes. If it would take until they're like 120, well then no, that's not reasonable for them to retire on. So the formula for compounding interest is, well, A would be your future value. P is your principal, so that'll be the amount of money you invest, multiplied by 1 plus the annual rate divided by how often it compounds, multiplied by how many years, times the end value again. All right, so most of this information we know, right? They want $500,000, so that's what the A value is. So 500,000. They are starting with $25,000. They're investing $25,000. That's the principal. All right, that's 1 plus the rate. The rate is 9%, so that's 0.09. And they're compounding monthly, so that is 12. And then again, the n value is 12. And what we don't know what we're solving for is the t. So we're going to see how many years. We're just going to solve for that variable. Once we solve for that t, that's going to tell us how many years it's going to take to turn $25,000 into $500,000. So what we're going to do to start is divide the 25,000 from both sides. All right, and then that number is going to be 20. So if we're trying to solve this exponential equation, think back to that flow chart, think back to the examples we've done. Is there any way you can turn 1 plus 0.09 over 12 into like a number that would be 20? No, right? So we're going to do that second way, which is just take the natural log of both sides. Power property is going to get the 12t out front. So you got natural log of 20 is equal to 12t times natural log of 1 plus 0.09 over 12. So now I'm going to divide that natural log from both sides. So now I've got natural log of 20 divided by natural log of 1 plus 0.09 over 12 equal to 12t. So that means t equals, I'm going to give myself more room here, natural log of 20 divided by natural log of 1 plus 0.09 over 12, all divided by 12. So does that answer our question? Technically, that is the exact answer. However, I don't know what that number is, right? No one would. So we're going to use our calculator to estimate this. So after estimating, that gets us to 33.41 years. So if they were 20 when they invested the $25,000, and you add that amount of years to it, they're only going to be 53.41 years, roughly, right? So that would be a reasonable ages to retire, right? So the answer would be yes, it is possible. All right, let's look at the next one. So how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? Essentially, it's the same question we just answered, just different numbers, right? So the 3,600 is what you want it to be. The 1,000 is what you're starting with. The 8% annual rate is that. Compounded quarterly means the n value is 4, and we're solving for t. So the first thing they're actually working through and solving and getting 1.02 in the parentheses. You can do that, or you can just type it all in that way in your calculator. It makes no difference. Although I guess it would make less work when you're writing that number multiple times. Anyway, then you divide the 1,000 from both sides, and you get 3.6 is equal to 1.02 raised to the power of 4t. Take the natural log of both sides. Power property gets you 4t on the outside. Divide natural log of 1.02 and 4 from both sides, and you get approximately 16.2. So it would take 16.2 years to turn $1,000 into $3,600 at a rate of 8% compounded quarterly. All right. Last question. How long will it take to double an investment earning 6% per annum, means per year, compounded quarterly? All right. I'm sorry, it's not the last question. I think we have one more after this. Anyway, so A equals 2p. So there's two ways to look at this. The value that you're going to have at the end is going to be double what you started with, right? So you can say it's equal to 2p. Principal is what you start with. So if you double your money, what you end up with is double what you started, right? And you can also use the formula for compounding periodically. So you can just use now the formula 2p is equal to p times 1 plus r over n times raised to the power of nt. Divide p from both sides. Now we can substitute in the information we have. So 6% is 0.06 there. Compounded quarterly is 4 for n. And then take a natural log of both sides. Use power property to get 4t up front as multiplication. Actually calculate what's on the inside there, which is 1.015. Divide that from both sides, and you get that t is approximately 11.64. So compound it quarterly at 6%, it would take a little over 11 and a half years to double your money. So find the time it would take to double your investment if the interest is compounded continuously. It's just a slightly different formula, right? For compounding continuously, it's A is equal to P times E raised to the power of RT, right? So you can set it up the same way and say, all right, well, A, if I double it, it's going to equal 2P, right? Or A is going to equal the formula for compounding continuously. So now I can say 2P is equal to P times E raised to the power of RT. Divide both sides by P, you get 2 is equal to E RT. Take a natural log of both sides. All right, use power property. Natural log of E. Remember that natural log means base E, so the exponent you put on E to get E is 1. So natural log of E is 1, so I don't need it anymore because 1 times RT is just RT. if I'm solving for t, now I just divide by r, and you get that t is equal to natural log of 2 divided by r. I'm assuming this question is going to be using the same rate that we used for the previous question. So let's just assume that. So t is equal to natural log of 2 divided by 0.06. Now we're going to calculate. And you end up with roughly 11.55 years. So not that much different than compounding quarterly. All right. Yeah, since it's a half day, just hopefully you got through the notes, and then we'll do the exit ticket in class tomorrow. All right, let me know if you have any questions.